Okay, so this is the second video for the queuing lectures. We went through the standard queuing models for a simple example in class, and I did that in the first video of this sequence too, where we looked. I think it was an example of a bunch of cars arriving at 8 o'clock in the morning to a gate. So they were arriving at a certain rate and being processed at a certain rate, and we looked at the deterministic approach to estimating average queue during the hour, and also the average delay experienced by the users. Okay, so I had said that this also applies to, or was applied to, the signalized intersection delay models that are used in the Highway Capacity Manual. And I want to show you just quickly how that fits here. So I'll go through that, and then in the next video, one more video, we'll look at shock waves. So here is the arrival, well, actually, it's the vehicle time curve that I used the last time. So this is the total number of vehicles arriving. This is the time during which they're arriving, and we have two curves. An arrival curve that is we're assuming is deterministic, so it's a constant rate of arrival from time zero. And we also have a departure curve, so the departure is equal to the arrival up to the point at which a signal turns red, right? And then theoretically there's an instantaneous change, and the departure curve then looks like this. So there's nobody leaving the intersection during red, and then when red goes green again at this point, they start leaving at a much higher rate because they're all queued up, right? So that much higher rate is the saturation flow until equilibrium is met, and they go on at the arrival rate beyond this red time. Okay, so this area within the two curves, the arrival curve and the departure curve, is the area that we talked about the last time. Okay. So if we can find that, we can calculate the average queue and the average delay for this situation. Okay, so let's say the example that we'll use is an arrival rate of 720 vehicles per hour. We have a cycle length of the signal of 60 seconds. Green to cycle length ratio is 0.5, therefore. Well, not therefore, it's given. So the green is 30 seconds. And the saturation flow is 1,800 vehicles per hour, we'll say. Okay. So let's find the average queue length and the average delay during a 1 hour time period, peak hour. So the slope is 720 vehicles per hour, 12 vehicles per minute. The saturation flow, the exit flow, is 30 vehicles per minute. Red time is 30 seconds, or 0.5 minutes. Okay. Okay, so from that, we want to calculate the area under this curve. Okay. And it looks like this. So the first step would be to find the height of the triangle so that we can find its area. Okay, some simple geometry. If we set out what the variables are, the unknowns are, we've got 0.5. We've got and then we've got an extra distance here from the end of red to the end, to the end of queuing, where the two curves meet again, okay? And the height, which is the total number of vehicles that have arrived during that time period. Okay, and Q is 12, S is 30, And where do those two slopes meet given this situation? Well, we can set up some scenarios here. So Q, this Q value 12, is equal to the rise over its run, right? And I can solve for H in that way. And similarly, I know that this slope is equal to the rise over its run, which is H over X. Solve for H, and then put them together and come out with X equals 1/3 minute, and plugging back in here, H equals 10 vehicles. That's how many vehicles have arrived during this time period. So the area of the red triangle is 2.5. The total area over an hour, right? There are 60 cycles in an hour because the cycle length is 60 seconds. So the total area during the hour is 2.5 times 60, or 150 vehicle minutes. That's the total area under that between those arrival departure curves. So the average delay per vehicle then, we have 150 vehicle minutes divided by the total number of vehicles arriving in an hour, 720. So that's 0.208 minutes, equal to 12.5 seconds per vehicle. And the average Q per cycle is 2.5 vehicles. That's it. Okay, so this is consistent with the equation that's given for delay, or at least the uniform part of it, in the highway capacity manual. So we have a cycle length of 60, a G over C ratio of 0.5, and the V over C ratio of this, 0.8. So the delay equation in the highway capacity manual for just the uniform portion is this. If we plug in our numbers, we come out with 12.5 seconds, which is consistent, right, with what we saw from the previous discussion. Okay, and note that for calculating emissions and fuel consumption, one of the variables, in addition to the delay and the queuing, is this percent stopped. And if we assume that the vehicles will stop if they're delayed more than 10 seconds, we can use this setup here to estimate the number of stops, or the percentage of stops. Okay, so that's 7.5 minutes. Let me stop here, and we'll go on to shock waves in the next video.